Dear students, our next topic is X-ray diffraction analysis. So the nanoparticles can be characterized by several methods, and one of the method is X-ray diffraction technique. And first of all, what is diffraction? It is the bending of light waves when they are incident on an aperture. So due to the bending, a diffraction pattern can be observed with a maxima and several minimas. At the maxima, that means the intensity will be very high. Okay. Next, why we are using X-rays for the crystal analysis? X-rays are electromagnetic waves with shorter wavelength, that is in the range of 1 to 10 angstrom. In our case, if we take our sample's crystal structure, there is 3D array of regularly spaced atoms. Here, the separation between the atoms will be around 1 angstrom. So, in order to get a better diffraction pattern, we can use X-ray source. The wavelength of X-rays, it is the order of few angstrom. Okay. Therefore, the X-rays are used for studying the crystal structure of sample. For the analysis of crystal structure, we need to know the Bracks Law equation, Bracks equation. Consider an example. This is the two atomic planes of our sample, and we are applying monochromatic X-rays onto the sample. Take ray 1 and ray 2. Incident angle is taken as theta. This is the grazing angle, and both the rays are reflected from the points A and B respectively. Here small d, it is the interplanar distance, and here the path difference between the rays ray 1 and ray 2 is CB plus BD. That is, when you compare these rays, ray 1 and ray 2 is traveling additional distance of CB plus BD. Okay. Then this incident angle is theta, and this is the normal line. So this angle will also become theta. Similarly, this angle will also become theta. So we can write CB is equal to BD is equal to D sin theta. So the path difference is CB plus BD, which is equal to D sin theta plus D sin theta, which is 2D sin theta. In a diffraction pattern, the condition for maxima is lambda times an integer value, or the path difference is equal to n times lambda, where n is the integer number, n is equal to 1, 2, 3, 4, etc. So we can write 2D sin theta is equal to n lambda, and this relation is known as Bracks Law of X-ray diffraction. So this relation gives the condition for the maxima. Okay. And using this relation, we can find out small d, that is the distance between the atomic planes. Therefore, we can identify the crystal structure of the samples. Then the computer controlled setup for X-ray diffraction is called X-ray diffractometer, or XRD. Check the figure. This is the complete setup of XRD. This is the X-ray source. This monochromatic X-rays, they are focused to the sample. This is the incident angle or grazing angle. Then the diffracted waves, they are captured using a detector, and the detector will calculate the intensity of diffracted waves. Here the crystal can be rotated, and the grazing angle will be changed accordingly. So we can monitor the intensity of reflected rays. Now we can plot a graph between the grazing angle and the intensity of diffracted waves. These are the peaks, that is the maxima, where the intensity will be very high. Here the maximas are at angle theta 1, theta 2 and theta 3. This experiment can be repeated for different planes and different grazing angle. Okay. Here we know the Bracks relation, 2D sin theta is equal to n lambda, and if n is equal to 1, that is for the first order, d is proportional to lambda divided by sin theta. And for three different planes, we can write D100 is to D110 is to D111 equal to 1 by sine theta 1 is to 1 by sine theta 2 is to 1 by sine theta 3. Theta 1, theta 2 and theta 3, they are the angles at which we got maximas for those three planes. That is for D100, D110 and D111. Okay. Now we can compare this result with the known ratios of different crystal structures. Here I have taken three known crystal structures and their corresponding values. And if our result, our observed values, if it matches for any of these known values, we can predict the crystal structure of the sample. Okay. So this is the basic working principle of X-ray diffractometer. And please note, this diffractometer is also used to calculate the grain size, micro distortion, texture and crystal parameters or lattice parameters. Okay. The physical and chemical properties of the sample, it will depends upon the crystal structures. So it is very important to detect correct orientation, correct crystal structures. In the next class, we can learn about another technique, that is UV visible absorption spectroscopy. Okay. Thank you.